Today we are going to see memory management in operating system, introduction to memory organization, contiguous allocation. Program must be brought into memory and placed within a process for it to be run. Input queue is a collection of processes on the disk that are waiting to be brought into memory to run the program. User program goes through several steps before being run. Binding of instructions and data to memory. Address binding of instructions and data to memory addresses can happen at three different stages. Compile time, if memory location known a priori, absolute code can be generated, must recompile code if starting location changes. Load time must generate relocatable code if memory location is not known at compile time. Execution time, binding delayed until runtime if the process can be moved during its execution from one memory segment to another. It needs hardware support for address maps. Multi-step processing of a user program. A source program will be sent to compiler or assembler, which is called as a compile time, and object module, it will be converted to an object module, and it is linked with other object modules through the linkage editor, and the module will be loaded again to the loader in order to connect it with the system libraries. And these libraries are dynamically linked at the time of execution. So these dynamic linking libraries will be as in-memory binary memory image. So inside the memory, it will be stored as a binary image. Logical versus physical address space. The concept of a logical address space that is bound to a separate physical address space is central to proper memory management. Logical address generated by the CPU, also referred to as a virtual address. The CPU generated logical address can be known by the user, but the physical address which is generated by the memory unit is not known by the user. Logical and physical addresses are the same in compile time and load time address binding schemes. Logical is virtual and physical addresses differ in execution time address binding scheme. Memory management unit, hardware device that maps virtual to physical address. In memory management unit scheme, the value in the relocation register is added to every address generated by a user process at the time it is sent to memory. The user program deals with logical addresses. It never sees the real physical addresses. If you see this diagram, the CPU is storing logical data, which is in the logical address of 346. This 346 is known by the user. When it is sent to the memory management unit, the part of the memory which is already stored by system files is 14,000. So this 346 can be stored only after 14,000. So the actual memory space allocated for this logical address 346 is 14,346, which is the physical address in the memory. But the user knows only the 346 logical address, and he cannot be able to know the 14,346 as a physical address. So this is the mapping of CPU's logical address and the memory's physical address is made by the memory management unit. Dynamic loading. This concept actually is based on loading of data or addresses only, or any library files only at the time of execution. So this is not loaded until it is called. So inside your program, if you call any library function, then only the data inside the library, that particular library functions will be loaded in the space where you have called the library function. Say, for example, if math.h, if you're using the header file math.h in a C program, and you call sign function inside your code, and the code which is already stored in the memory for the sign function, maybe 5 or 6 lines, so that will be loaded in the place where you have called the sign function. So this type of loading this smaller code into your main program is called as a stub. So better memory space utilization is made and unused routine is never loaded. Suppose if you are not calling any of the routine, it will not be loaded. So this will help the memory to get better utilization. Instead of, suppose you have in math.h some 100 header files, and 100 functions you have already stored in the header files. It is not needed all the time, the 100 functions. Only the functions which is called is needed at the time of execution. So by this, the complete memory space utilized by the code, that 100 functions will be reduced to only 5 or 6 lines of the functions what you have called. So this is the better memory space utilization. This is useful when large amounts of code are needed to handle infrequently occurring cases. No special support from the operating system is required implemented through program design. So no physical device or any other software codes are needed for doing this dynamic loading. It happens automatically, or it is made by the memory automatically at the time of execution. And the next concept we need to know is dynamic linking. So dynamic loading is loading of that particular program at the time of execution. And what is a linking is the particular function will be directly linked to the place where it is stored. Instead of loading that particular 5 or 6 lines of that function, you can directly go to the memory space where your code is already stored. So this is called as linking. Dynamic linking is when at the time of execution, the linking happens. And this small piece of code is called as a stub that is used to locate the appropriate memory resident library routine. So instead of loading that particular 5 or 6 lines of the function, you are directly connecting the connecting the memory to, or connecting the code to the space in the memory where your function is loaded. So that's why loading and linking is different. Stub replaces itself with the address of the routine and executes the routine. Operating system needed to check if routine is in process memory address. The main work of the operating system in this part is it needs to check whether that particular routine is available in the memory address. Dynamic linking is particularly useful for libraries. When your program is not calling any of the libraries, there is no need for dynamic linking or dynamic loading purpose. Overlays. So this is a concept which will help to keep in memory only those instructions and data that are needed at any given time. Needed when process is larger than amount of memory allocated to it. So if you are using a process which has some memory allocation which is needed, but the memory space is very less for the process to be stored in memory. So implemented by user, no special support needed from operating system. So for this we have to write the coding in the operating system, and there is no any hardware support needed for this. But structuring of overlay when you're designing an operating system is very, very complex, because the lines of the code inside your program may be 100 or it may be 1,000. So the overlays concept should accommodate to the number of lines in the program. So this is a diagrammatic representation of overlays for a two-pass assembler. So in this, you can see that we have a code which is of memory space 70K, that is pass 1. And we have another set of code pass 2, which is of memory space 80K. But in your memory, already you have stored 20K of symbol table and 30K of some common routines, and 10K is definitely needed when you want to use the overlays. This overlay driver is a program which will make that particular code to store in the memory whenever it is needed. So here, suppose you want the pass 1. So at that time, the space after the overlay driver will be used for loading the pass 1. Suppose the user wants pass 2, pass 1 will be taken out from the memory, and that space will be allocated for pass 2. So this pass 1 and pass 2 can be repeatedly called by the user, and only one of that pass 1 or pass 2 will be in the space where your memory is allocated. So this is called as overlays. That is, whenever we are needing, we are calling that particular routine to be loaded into memory. And the next concept you want to see is swapping. Because when you talk about overlays, you need to know how it happens. When pass one is needed, pass one is loaded into memory. When pass two is needed, it is again loaded into memory after taking out pass one. So how it happens? The concept is swapping. So a process can be swapped temporarily out of memory to a backing store and then brought back into memory for continued execution. So what is backing store? Which is a fast disk large enough to accommodate copies of all memory images for all users. So there will be a direct access to these memory images. What is rollout and roll-in concept? So swapping variant used for priority-based scheduling algorithms. Lower priority process is swapped out, so higher priority process can be loaded and executed. So definitely we need some particular type of execution with the help of the priority assignment. You can assign both lower or higher priority for process. If the lower priority process is residing in memory and they are not called for the minimum number of or maximum number of time, what is given by the memory, and no other user is using that particular lower priority process, then the use of that lower priority process residing in memory is waste. So the space can be allocated for some other higher priority process which is needed by the CPU. So this lower priority process will be rolled out or swap out, and the higher priority process will be roll in or swap in. So the major part of swap time is transfer time. This is called as a transfer time. So total transfer time is directly proportional to the amount of memory swapped. That means the how much memory it is swapping. So that particular time of swapping time is the total transfer time. If it needs some 1 hour to transfer a particular process, the total transfer time is going to be 1 hour. So modified versions of swapping are also found in many systems. So this concepts of the rollout and roll-in can be seen in a better way in Unix, Linux, and Windows. So the recent versions have this modified version of swapping. And this is the schematic view of swapping. So the a main memory is here and a backing store is there. Backing store could be of anything, either pen drive or CD drive, or it could be a mobile phone where you are storing all your process. So you want to swap the process from the backing store into the main memory. So you can see that the main memory is used, particular spaces will be definitely used by the operating system, what you are going to use. If it is a Windows, some part of memory space will be allocated for the system files of Windows. And for if it is a Linux, some part of memory will be allocated for that particular operating system. So the remaining spaces only can be used by the user. So in this diagram, you can see that the first one is swap out. That means already in main memory, process P1 is there that has been swapped out, and process P2 is swapped inside the user space from the backing store. The swap out also happens, and the process P1 will be stored in the backing store only. So whenever needed, you are going to load process P1, and then you are going to swap in process P1 and swap out process P2 also if it is needed again. And what is contiguous allocation? So main memory, usually it is of two partitions. Resident operating system, that is the operating system what you are using, usually held in low memory with interrupt vector, and the user process then held in high memory. The space where the user process, our process are stored, is called as high memory. And what is single partition allocation? Single partition allocation is the relocation register scheme used to protect the user process from each other and from changing operating system code and data. The relocation register contains value of smallest physical address. Limit register contains a range of logical address minus each physical logical address must be less than the limit register. So we will see in the example diagram what is the limit register and what is the relocation register. So in this diagram, you can see that the CPU is sending some logical address, and the value of logical address, if it is less than the value of limit register, then it is a trap, that is addressing error. So for example, if you take uh, some logical address is going to be 400, but your program is actually going to store only 10 lines. Okay, so from 400, 10 lines of code you have stored, so it is 410. So what is the limit register? 410. Your program starts from 401 to 410, right? And suppose the user wants to know the line of 11th, that is the line which is not available in your programming code. So there won't be a 11th line in your programming code, but the user wants to know about the 11th line. So what is the limit register value is 11. So which is the logical address is going to be 410 only. So totally it is 410, but the limit register is asking for 11th line. So if it is not, it is less than the limit, the logical address should be less than the limit register. But it is greater than 11 is greater than 10. So therefore, it's a trap. So it will show an error which is called as an addressing error. But everything is fine. When the logical address is less than limit register means the process can be continued. If it is greater than the limit register, that is 11 greater than 10 means, then it is not possible. So when it is less than the limit register, so we can go for the relocation register. So actually your program stores in 401 to 410. So the relocation register will contain 10, and the logical address which is given by the user is 400. That is the starting address of your program. The limit register is only 10 lines. That is, the limit register value is 10. So it is possible for the relocation register to move to the position of 400, 410. So we can go to the memory with that 401 to 410. Physical address will be added, and the memory will show you the content of that particular program, which is needed by the user. And multiple, this is for single partition. So when you go for multiple partition allocation, so what happens is your concept called hole happens, which is a block of available memory. The holes of various size are scattered throughout the memory. So a hole is nothing but the place is empty. So no process has been allocated to us. That is called as a hole. So when a process arrives, it is allocated memory from a hole large enough to accommodate. Suppose a process comes with 30K byte, and already you have a hole of 40K byte. Even though you have a space of 40K byte, it needs only 30K byte. But the 40K byte will be allocated for that 30K byte of your program. So that is a large enough memory space allocated to your program, because 10K is not going to be used by your program. It is a waste of memory size. Okay. So operating system maintains information about allocated partitions and free partitions. Free partitions or whole partitions. So you can see in the diagram, you have a process 2, process 8, and process 5. When process 8 is taken out from the memory, the process 8 space is already there. And process 9 now comes, and that is allocated after process 5. And after that, process 10 comes, and that will be allocated after process 9, because all these are the whole part. The space where process 8 stored, and it is now replaced. So that space is a whole space. So in that whole, you are providing spaces for 9, process 9, and process 10. But still, you can find some more spaces available in the last diagram. Some more spaces are available to load some more processes. So this is a whole now. So you can allocate, when the memory gets a process, it will allocate that into this whole. And dynamic storage allocation problem. So what is this problem is, when a process comes, how to allocate the process inside the whole of a memory. how to allocate the process inside the hole which is available in the memory, because the memory is having the details about the holes available and also allocated process. So with that, it needs to check the necessity of the memory space of the process comes, and it needs to allocate it. So in that allocation, it may happens based on first fit, best fit, and worst fit. So what is first fit is, whatever the memory space is needed, don't see it whether it is going to waste the memory space or not. You allocate the process in the first space, whatever you see in the first hole, whatever you see in that memory. That is, even though it is big enough, that is called as first fit. So we are not taking any conditions or something, or we are not checking anything that whether the whole is correctly allocated or not, or whether the memory space which is wasted can be used for some other process. We are not going to check anything. Whenever we see a empty space, we will allocate that process into that empty space. And what is best fit is, allocate the smallest hole that is big enough. So a process comes with 30K. So you are having 40K space of a hole and also 80K space of a hole. In that, you are going to allocate it in the 40K space of the hole. That means it is the smallest hole which is available, but it is the biggest hole for the process, because the process needs only 30K, but it is allocated for 40K. So 10K is wasted here. But even though you had 80K, you haven't chosen that 80K. So what happens if you have chosen that 80K? So totally 50K will be of wastage of memory. So you are saving that 50K here. So that's why this type of fitting is called as a best fit. And what is worst fit is, allocate the largest hole. So you have a 30K process to allocate, but you have 40K of hole and also 80K of hole. You don't need to worry about anything. You directly allocate it to the biggest hole. So 80K will be allocated for 30K process. So the remaining 50K is wasted here. So that type of allocation is called as a worst fit allocation. So the first fit and best fit better than worst fit in terms of speed and storage utilization. So why? In the first fit, you have the searching of that particular process will be very easy. So totally, if you have a 5 process, and in the third process space itself, you have allocated the new process, means the searching of that new process is taken only for 2 process to be checked. So when you come for the third process, you can identify the process you want to search, because you have allocated not at the last, or you have allocated not in the middle. So you have allocated in the first hole that is big enough itself. So therefore, you can search the particular process very easily. And when you go for best fit also, instead of searching the bigger size, I am going to search only the smaller sizes which is greater than the process allocated. So that is also very easy for finding that particular process. And what is fragmentation? So when the allocation happens in memory, and when you have a holes possible, means definitely fragmentation is also possible. So you have 2 types of fragmentation: external fragmentation and internal fragmentation. So what is external fragmentation? Total memory space exists to satisfy a request, but it is not contiguous. That means you have holes. Suppose a process 30K to be allocated, but you have holes of 5K, but not repeated. That is, it is not contiguous. So it's in different places. Then you have to split up your process into 5K and allocate it in those holes, which are not together. And that is called as external fragmentation. And what is internal fragmentation is, allocated memory may be slightly larger than requested memory. So the memory which is allocated may be slightly larger than requested memory. This size difference is memory internal to a partition, but not being used. That means the example is 30K process is coming and I'm allocating to 80K. So that is the biggest memory I have allocated. This 50K is called as a internal fragmentation. So the hole which you create when you are allocating the process, with that you can say whether it is the internal fragmentation or external fragmentation. When you get a process, and you're allocating it sophisticatedly, all the lines of the process in the same space, then you will get a external fragmentation. Um, if it is the same space, it's the internal fragmentation. But when you're allocating this 30K of process in a split up way, then that is called as a internal fragmentation. So reduce external fragmentation by compaction. So you have to compress the spaces which are free, so that you will allocate the best space for the process without any fragmentation. So the shuffled memory contents replace all free memory together in one large block. So what you can do is, the first step is you have to shuffle the memory spaces which are free enough. So combine all the free memory spaces, all the holes together, and make it as a larger size block for processing. Or compaction is possible only if relocation is dynamic and is done at execution time. The IO problem, the problem which you have, the latch job in memory while it is involved in IO. Do IO only into OS buffers. So IO problem is when the process wants to, any process wants to read another process that is you have stored in the memory in any hole. So it needs to search according to either first fit, best fit, or worst fit which has been used. And also the process searching affects with the fragmentation that has happened. So when you reduce this external fragmentation, the IO problem can be reduced. And the next topic we are going to see is non-contiguous paging, segmentation, virtual memory, and page replacement algorithms. What is paging? Logical address space of a process can be non-contiguous. Process is allocated physical memory whenever the later is available. So what is non-contiguous? There won't be a continuous space which is available for a process to allocate. Then it is a non-contiguous space. So divide the physical memory into fixed size blocks called frames. Size is power of 2 between 512 bytes and 8192 bytes. So divide the logical memory into blocks of same size called pages. So you know what is physical memory, you know what is logical memory. The physical memory is the actual memory in the uh, CPU. So, and what is logical memory is the memory which is seen by the user. The user thinks a memory, imagines a memory, that is called as a logical memory. So this logical memory needs to be divided into pages, and the physical memory needs to be divided into frames. So we are fixing a block like say for example, if you have a 100K memory space in physical address, you divided it into 10Ks so that you can allocate the process which comes less than 10K. And also if you get any process which is greater than 10K also, it can be allocated continuously. So you don't get fragmentation problem also. So for this, we are going to use the technique paging, which divides the physical memory into frames and divides the logical memory into pages. So how will you connect these pages and frames? So you are going to have some address, and with that address mapping happens so that you can able to find which frame, which page is located in which frame, and keep track of all free frames. To run a program of size n pages, need to find n free frames and load program. So only when you have n free space for n size pages, you can store it in the physical memory. Otherwise, you're not able to store it. So for example, you have 10 pages in the logical memory, but you have only 8 spaces available in the physical memory. You cannot store that uh, program into the physical memory. So set up a page table, so which is going to tell you about the free spaces of physical memory and also the frame which is allocated to the physical memory. So this page table will help you to translate the logical memory into physical address. So which page is stored in which physical location, physical address, you can find it with the page table, as we have index columns in our books. So that index columns contains the content and also the page numbers. So internal fragmentation is sometimes this internal fragmentation is possible in paging. So we will see how. And address translation scheme. So what are the addresses used by the CPU in the case of this type of paging technique? So it uses two types. One is page number, another one is page offset. Page number is the index into a page table which contains base address. So you are going to have a base address of each page. Say, for example, you have a process and the process gets started from the location or physical address of the memory is 14,001. So the base address is 14,001. So you are storing 10 lines of that page in 14 until 14,010. So what is the base address of that particular program? It is 14,000. And what is page offset? Combined with base address to define the physical memory address that is sent to the memory unit. So with that base address, you are going to connect the 10. When you add the offset value, that is how many lines you have in that program, 10 lines. So when you add 14,000 with 10, 14,000 is the base address and 10 is the page offset. So when you add it, you're going to get the actual final address of the program. So your program stores from 14,001 1 to 14,010. So this is called as page offset. So you can see the address translation architecture. So you in the CPU, you are going to give the physical address and the page offset is D. So the physical address you have given, you have given the page number and the page offset D, P and D. So you're giving a logical address with the page number and also the offset D. So what happens is it needs to match the offset of the physical address and it needs to find in which frame that particular page is stored. So how will you find it? You have to use the page table of the memory in order to see where your page is stored in the corresponding frame. So that will be searched in the page table and it finds that particular frame is stored in the place where F is the content. And that physical address F, the address of F will be, physical address will be added with the offset. So this is going to tell you, see, I am telling you the page address as 10 lines. So 1 is the starting address and the frame where the physical address is stored for your program is 14,000. So this 14,000 is added with the offset. So you want to know that from the 10 lines, you want to know about fifth line. So you are sending the value as 5. So the physical address is 14,000, which will be added with the offset, that is 14, that is 5. So 14,005 is the position where your fifth line of your 10 lines program is stored in the physical address. So once again, I'll tell you. So the CPU is going to give you a logical address with the page number and the offset. Okay. So this page number is taken to the page table and it will search the corresponding physical address of the physical address which is stored in the page table, that is F, and the F will be added with the offset D and the actual address it is going to find. So I'll tell you an example. The page, you are having a program with a page of 10 lines and you are sending, if you want to know about the fifth line, so the offset is now 5, that is D is 5. The page number is 14,000 is this base address. So you are giving the base address as 14,000 where your program is starting in your physical address. So it will find in the page table that 14,000 is the starting address, that is F. So this F value will be added with the D offset. So that is, you want to know the fifth line. So 14,000 plus 5, it shows the 14,005th location where your fifth line of your 10 line program is stored in the physical memory. So this is another example given for paging. So you have 4 pages from page 0 to page 3 in logical memory. And you have a page table which contains the address of the physical memory. So you can see that in the page table. For page 0, the frame address is 1. So when you go to the physical memory, you can see the frame number. So that is in the first frame, the page 0 is actually stored. And when you go for the page number 1, and it is stored in the fourth frame. When you go for the fourth frame of your physical memory, you can see that page 1 is stored. Similarly, page 2 is stored in the third frame. So you can check it in the third frame, page 2 is stored. And similarly, page 3 is stored in the frame 7. When you go for frame 7 in the physical memory, you can see the page 3. And sometimes you may be storing more number of lines instead of a single line in your physical memory. So if you are using like that, you can check the page table like this. So you can see 0, 1, 2, 3, which contains some value of A, B, C, D, and 4, 5, 6, 7, which contains the value of E, F, G, H. And similarly, 4 parts of pages are available. So each part of the page is stored in which frame. You can see it in the page table. So the part of 0, so the 0 is the starting address of A. So 0, when you check the frame number, it is 5. So when you go to the frame number 5 in the physical memory, you can see that the page 0 value will be stored. See, this is that is in fifth frame. So how will you find the fifth frame here? This is first frame, second frame, 8 is the third frame, 12 is the starting of the fourth frame, and 16 is the fifth frame, and 20 is the sixth frame. So when you start from 0, 20 is the fifth frame. So the fifth frame will contain the ABCD value. So you can say that 20 which contains the ABCD value. And when you go for the second one, so it is stored in the frame of sixth frame. So you have to check 0th frame, 4 is the first frame, 8 is the second frame, 12 is the third frame, 16 is the fourth frame, and 20 is the fifth frame, and the sixth frame contains the page group of pages in page 1. So what is page 1? EFGH. You can find in the sixth frame, the EFGH is stored here. So likewise, you can find the pages of the frame corresponding frames. You can find it in the page tables. And what are free frames? Free frames are the frames which are not at all allocated. So how will you find the free frames? So before allocation, it was empty. You can see in the diagram, it was empty before allocation. No frame has been used. So the free frames given here, I think